Today we're going to learn about section 6.6, standard enthalpy of formation and reaction. In the last video we had this equation right here, that the heat of reaction is equal to the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants. And now we're going to learn how to use that equation. A couple important things. First off, the standard heat of formation, that's this delta HF naught, standard heat of formation is 0 for pure elements at 25 degrees Celsius in their standard states. And then I've put a big table of heats of formation that I obtained from the internet. And one of the important things that you need to know is this piece right here. These values, all the values in this table, are determined experimentally. And then they're put into these lovely data tables, and we use them for solving thermodynamic problems. So we're going to use this data for some problems. Some important things to note before we go into this is the units for standard heat of formation are kilojoules per mole. Sometimes they're in kilocalories per mole, but we're going to be using joules for our energy units. So we are going to calculate the heat of reaction for this reaction given right here. The first thing you want to do when you are trying to find a heat of reaction, if you're given heats of formation, these heats of formation right here, if you're given heats of formation, you can put the values of the heats of formation above the reactants and products and use that to do your calculation. So here we go. We've got our methanol, CH3OH. We look that up right here. We see that is negative 238.6, and that's kilojoules per mole. Oxygen is not in our table. Why not? Because of this note right here, pure elements, heat of formation of 0 if the pure element is at 25 degrees Celsius in its standard state. Well, oxygen at 25 degrees Celsius, hopefully you all know oxygen is indeed a gas at 25 degrees Celsius. So this is the standard state of oxygen. So this has a standard heat of formation of 0. CO2, let's look up CO2. Here we go, right here, negative 393.5. And now the water, you have to be very careful. Make sure that you are looking at the correct phase, because if you look at the table, we've got water and water vapor. H2O liquid, H2O gas. We want the liquid form for water, so we will use the value that's negative 285.8. And now we're just going to use the the equation right here, that the heat of reaction is the sum of the heats of formation of the products minus the reactants. And we have to multiply by coefficients. So I've just rewritten the equation that was up at the top. And now I'm going to substitute in all of my numbers right here. Notice for this piece right here is this piece right here. That's negative 393.5 kilojoules per mole. And I multiply that by 2 moles because this coefficient of 2 right here represents 2 moles. And then you see the moles cancel out, and I end up with just kilojoules. I have to do all the products. So there's another product over here. I've got my water value of negative 285.8 right here, kilojoules per mole, and I've got my 4 moles. So I multiply that by 4 moles. And I now subtract off the reactants, minus 2 moles, because I have 2 moles right here. And the value for this methanol is negative 238.6. I put that in here. And when I calculate that all out, this is what I get. So there's another problem. And I've been asked by some students to tell you when to pause. So I want you to find the heat of reaction for this reaction. I'm going to tell you to pause. I'm not going to go through every step. I'm just going to put the solution up. When you unpause this, you'll see the solution in a moment. Just some quick notes. You can use all the heats of formation on that table and use those to actually solve the problem. And so you should pause now. Okay. Oh, well, let's look at the answer, and I will point out some places where you might have gotten something wrong. So, if you did not get the same answer that I got, it's possible I did it wrong, but there's a few key places where students make errors. Right here, did you check to make sure that when you looked up your water, you used the gas phase water number? So, water vapor has a heat of formation of negative 241.8, not negative 285.8. So you want to make sure you use the right value for the water. The other place where students have issues is when you're subtracting off the reactants, students forget to distribute this negative right here. So you might want to check your math if you got this wrong, again. Check your math and see if you remember to add all of this up and then subtract all of that from the products, because it's all the products minus all the reactants. Okay, we're going to move on to Hess's Law. So here we have a statement of Hess's Law. Hess's Law basically says if you're going to add two reactions together, the heat of reaction for the added reactions is equal to the sum of the heat of reaction of each single reaction. That doesn't make a lot of sense to a lot of students. You have to see an actual problem to understand this. So let's just look at an example here. Suppose I have reaction A and reaction B, and I add those two reactions together. Hess's Law says I should just add up the delta H's. So if I put the two reactions together, reaction A plus reaction B, the delta H for that new reaction will be 13, 5 plus 8 kilojoules. Okay, that's still sort of abstract. We're going to make it even more concrete. But first I want to tell you a few consequences of Hess's Law. First is, if you multiply a reaction's coefficients by a number, you have to also multiply the heat of reaction by that number. And I need to put that in there. Okay, and the other consequence is if you reverse a reaction, you have to multiply the heat of reaction by -1. Reverse means, when we say reverse, we're turning the products into reactants and the reactants into products. So what does this look like? How do we apply this? We're going to use this for the following problem. We're going to use the three given reactions right here to find the heat of reaction for this. We're trying to find delta H. And these are all standard conditions. Okay, what you do in these problems is you try to find where the chemicals in the reaction you're looking for, where they are in the reactions that you're given. So let's start with CO2, and we're going to look at our three reactions. Can you see which of the three reactions has a carbon dioxide in it? Hopefully you're noticing it's right here. And you might want to use colored pens or pencils for this part because it's good to be able to visualize where the chemicals are coming from. So in the reaction I'm trying to get to, I need 3 carbon dioxides. And in the given reactions, I have 1 carbon dioxide, but it's a product, not a reactant. So first off, I need to multiply this by 3, multiply everything by 3, and I also need to reverse it. Reverse means I'm going to make my reactants products and products reactants, although I said that reverse. So the reactants here become products, and the products here become reactants. So we said if we multiply our reactions coefficients by a number, we have to multiply delta H by the number. And if we reverse a reaction, we have to change the sign of delta H. So it's like we're saying we're going to multiply reaction 1 by -3. So we have to multiply delta H by -3. Now, one very important rule. I'm going to write it down and then I'll say it. So I actually gave you two important rules. First rule, not that. Number one, if you see a chemical appearing in more than one of the given reactions, you should ignore the chemical. In this case, if you look at these three reactions here, oxygen appears twice. We're going to ignore the oxygen for now, meaning we're not going to work with this oxygen in the reaction that we're trying to get to. We're going to just ignore it and hope everything works out. So anytime that a chemical appears in the reaction you're trying to get to, if that chemical appears in more than one reaction, just ignoring it for now. We're not going to use it to figure out what we multiply or reverse for a reaction. And the second rule, very important, if you have already used a reaction, don't use it again. Assume everything will just work out. Okay, so let's go back to finishing up this problem here. We've already done the CO2, now we'll look at the waters. Let me erase the oxygen real quick so we don't have different blues all over the place. So we've got 4 waters that we need as a reactant, and we look at our 3 reactions, and we see that water is right here, and water is a product. I don't need water as a product, I need water as a reactant, so I'm going to have to reverse this reaction, so I'm going to change the sign of delta H. And I also have to multiply this reaction by what? By 4. So I would have a 4, the 1/2 would become a 2, because 2 times 1/2 is, 4 times 1/2 is 2. And I'll have a 4 here. Okay, I need another color, so let's grab a new color. Now I've got this propane. C3H8 is propane, and I look for my reaction. Where do I see propane? Ah, propane's right here. Oh, I forgot to multiply delta H by 4. If we multiply the reaction by 4, we have to also multiply delta H by 4. Okay, let's get back to propane. I'm not sure which color I used. Let's see. Oh, it's close enough. Okay, so propane is a product in the given reaction, and it's a product in the reaction we're trying to get to, so I don't need to change the sign. I'm not reversing the reaction. And I have only one propane here, and I have one here, so I don't need to change anything. I'm just going to have one of those. So I will leave the coefficients as is. So this stays a 3, this stays a 4. Okay, so that is telling me now that the delta H for this reaction will be -3 times -236 minus 4 times -171 plus 1 times -62 kilojoules. Okay, so that's easy enough. Just -3 times -236 minus 4 times -171 plus 1 times -62. However, we want to check and make sure that this is all going to work out. So in these problems, you have to always rewrite the reactions with whatever that you've done to them. So reaction 1, hang on, I'm going to erase everything that I did in here so you can see what's happening here. I still have the information under the delta H's, what I need to do to each reaction. So I need -3 of reaction 1. So I'm going to rewrite reaction 1, multiplying it by -3. And I'm going to use red for that one. So I'll have 3 CO2s makes 3 C's plus 3 O2s. Okay, so I reversed and multiplied by 3. Next reaction, reverse, multiply by 4, and I will write that in blue. So 4 waters. Oops, that was not written correctly, and I'm about to get the wrong thing. Sorry about this. Okay. My goodness, the board is not cooperating today. We might be slightly misaligned. We have 4 waters. You usually do have to take care of looking at whether you have things in the correct phase, the gases and the liquids. For now, I'm going to ignore that because I'm going to assume everything is in the correct phase. There are times when they're not, but for now, we'll just assume everything's in the correct phase. So 4 waters makes 4 H2s and 2 O2s. Okay, so that was multiplying the second reaction by -4. And the third reaction I leave alone. And here we go again with that screen. Sorry about that. Okay, the third reaction I leave it as is. Where did it go? There we go. 3 C's plus 4 H2s make C3H8. Okay, so I've done everything I did to the reactions, and now I have to add everything up. Well, my goodness, we've got a lot going on here. First off, you want to think of these arrows here as an equal sign. And if we're adding things up and we have equal signs, we can cancel things that are the same on the left side and the right side. So I will use a new different color to show. Do you notice we have 4 H2s here and 4 here? Those are on opposite sides of the arrows, so they're going to cancel out. And I will look for anything else that will also cancel out. We'll use a different color. No, that's not a good color. Do you notice these 3 carbons here and the 3 carbons here will also cancel out? Anything that's on the left side of the arrows that's the same as something on the right side of the arrows can cancel out. Anything else? I don't think anything else can cancel out. So now I've got my 3 CO2s, my 4 H2Os makes, what's on the right side now? I have my C3H8. I can put these oxygens together to give me 5 total oxygens. And I check, do I get back the reaction that I was looking for? Did I get back 3 CO2s? Yep. 4 H2Os, yep. A C3H8 and 5 O2s. Yes, I do. So there's my reaction. So now let's go ahead and calculate delta H. So delta H will be, it's going to be -3 times -236 minus 4 times -171 plus -62, and that's 1,330 kilojoules. Now let's just talk sig figs real quick. Notice in all the numbers I was adding, they were written to the ones place. They were precise up to the ones place. So I have to keep my answer up to the ones placeholder, so I leave this as is. Okay, we're going to do a couple more of these. I know these can be confusing, so if you're a little frustrated, don't worry. It's normal. Hess's Law gets a little confusing. So let's do another. Okay, so here's a new problem. We're trying to find delta H. Oh dear, sorry about that. We're trying to find delta H for this reaction right here, given the first 2 reactions. So again, we want to identify what's in this reaction we're trying to get to that's in the first 2 reactions. So NO2, where is that? I see it. Do you see it? It's in reaction 2, right here. And what do I have to do? Oh, by the way, you can pause this and do it on your own if you want to. Totally up to you. I need to reverse the reaction. I'm going to multiply this by -1. And notice the coefficient 2 and 2, it's the same. So I don't have to multiply that reaction by anything. I just need to reverse it. Now I'm going to check my other chemical. Oh, I already had green. So let's check N2 over here. Do I see N2 in any of my reactions? I sure do. I see it right here. And again, it's on the wrong side. The nitrogen I want is a product, but it's given to me as a reactant. So what do I have to do? I have to reverse the reaction. Multiply by -1. Okay. Now, I've also got some oxygens here. And I haven't dealt with those yet, but one of the notes I wrote to you, the important rule is, nope, those aren't our rules. Where's our rules? Here we go. Rule 2. If you have already used a reaction, don't use it again. Assume everything will work out. So, I've already used reaction 1 and I've used reaction 2. I've got to just assume the oxygens are going to work out. I have to hope for the best. So now we check. We're going to check to make sure that the reactions add up correctly. So I reverse the first reaction. So N2O4 makes N2 and N2O2. And I also had to reverse the second reaction. That -1 means reverse it. So I have 2 NO2s making, what do we make? An N2O4. And I have to add those reactions up. I first check to see if there's anything that I can cancel, and hopefully you notice the N2O4 on the left and the right, they're the same thing. And these arrows here, they're kind of like equal signs. So I get to cancel out my dinitrogen tetroxide. And now I will add everything up. I have 2 NO2s for my reactants. I have an N2 and 2 O2s left over for my products. And is that the reaction I was looking for up here? Indeed it is. So now I can calculate my delta H reaction. I'm just going to, whatever I did to the reactions, that's what I do to delta H. So I need -1 of these, so I have -6 kilojoules. I have -1 of this, -35 kilojoules. And I end up with -41 kilojoules. So my reaction, delta H, is -41 kilojoules. That joule looks really goofy. So quick note on sig figs. We don't look at this delta H and say it has 1 sig fig, so I have to keep only 1 sig fig. We're adding, so we look at placeholders. This delta H for reaction 1, 1's place. Reaction 2, the 1's place. I keep my answer to the 1's place, and my answer is fine, -41 kilojoules. One more problem, you can pause, try it on your own, or there's a little trick to this one, so you might want to follow me along. I suppose I should have said follow along with me as opposed to follow me along. All right, let's move on. So another problem, same concept. Let's erase that. Okay, and this one is tricky. You'll see why pretty quickly. So we're going to check our iron. We're trying to get delta H for this last reaction down here, given the first 3 reactions. So the iron, let's see, I only see iron by itself right here. Now, I want how many? I want only 1 iron, but in my reaction that I'm given, I have 2. So what do I have to multiply delta H by? 1/2. 1/2. I'm not going to worry about multiplying all the reaction coefficients yet. I'll do that at the very end when we're checking. So I know I have to multiply reaction 1 by 1/2. And what else? Is the iron on the correct side? No. Reverse it. So it's -1/2, not just 1/2. Okay. CO2. Let's see. CO2 is, where do I see my CO2? Oh dear. I see CO2 in 2 places, and what I remember is Dr. Udell told me, I was talking to myself, and I told myself, sorry, I'm being a student in class. Okay, I told everybody, if you have already used a reaction, don't use it again, assume everything will work out. That doesn't apply so much here, except we've already used reaction 1. More importantly, this one right here. If a chemical appears in more than one of the given reactions, ignore it for now. So, oops, okay. The CO2 is appearing in 2 reactions. So I've got to ignore my CO2 right now. It's a little complicated. You will learn how to do this. Don't panic. But for now, it's too complicated. We're not going to worry about it. So we'll switch to another chemical. We use blue. All right. Let's extend this. So FeO, I'm going to hope that that's only appearing in one place. And you got to be careful, there's FeOs all over the place. Here, oh my goodness, you know what, let's go back a minute. The CO2s, now I'm noticing, there was another place where we had CO2. I do not want to deal with those CO2s at all. It's in every reaction, it's going to be ugly. So, back to the FeO. FeO appears in the reaction I'm trying to get to. And I believe, yeah, I'm good. It only appears in reaction 3. Whew, we're lucky there. So I need only one FeO, but in the reaction I'm given, I have 3 FeOs. It's on the correct side, so we're in luck there. But what do I need to multiply this by? You got it, a third, because a third of 3 is the one that I'm looking for. Okay. One more chemical here that we can focus on, carbon monoxide, CO. Where do we have? We got some CO here, some CO here, some CO there. My gosh, it's in 3 reactions. So now this is where it gets tricky. This would be an extra credit problem on a test. When it gets this complicated, I do not give these out as just regular problems. In AP Chem I would, but not in Honors Chem. So let's figure this out. I'm noticing that, I'm going to switch colors again. We're going to look for how can we make this reaction, adding these reactions, 3 reactions, look like what I'm trying to get to. And I notice this Fe2O3 does not appear in my final reaction. So I've got to get rid of the Fe2O3 somehow. And I see that the only other place where that occurs is right here. So I know because of the -1/2 right here that I've got 1/2 of an Fe2O3 on the product side. It's hard to see that. It says products over there. Okay, so because of this reaction right here, with a -1/2, I've got 1/2 of an Fe2O3 on the product. So I need to get rid of 1/2 of an Fe2O3 from the products, which means I need to put 1/2 of an Fe2O3 on the reactant side. So I'm going to have to multiply this by a negative number to get this Fe2O3, iron 3 oxide, over on the reactants. And I need 1/2 of them. I have 3. How do I turn 3 into 1/2? What do I multiply 3 by to get 1/2? One sixth. That seems really strange, because 3 divided by 6 is 1/2. Wow, this is really ugly. But now I've used every reaction once, so I'm not going to worry about the CO2 or the CO. I'm going to just hope that they all work out. So let's see. Let's see if this all works. Okay, I had to multiply the first reaction by -1/2, and I'm not going to do the reactions all color-coded at this point. So I reverse. I'm going to have 1 Fe. I'm going to have 3/2 of a CO2. I'm going to have 1/2 Fe2O3 and 3/2 of a CO. Second reaction, -1/6. I got to reverse it. Multiply everything by 1/6. So I've got 3/6 or 1/2 of an Fe2O3. I've got 1/6 of a CO. And I have 2/6, which is 1/3 of an Fe3O4, and 1/6 of a CO2. I just multiplied straight across the board. Okay, for reaction 2. Now reaction 3, I'm going to need to multiply by 1/3, and I'm not reversing. So reaction 3, 1/3 of reaction 3. I get 1/3 of an Fe3O4, 1/3 of a CO. Let's see, I get 1 FeO, and I get 1/3 of a CO2. Ooh, not fun. Let's see, does anything cancel? I know that this is going to cancel because I made sure that would happen. So my 1/2 Fe2O3 cancels. And switch colors. How about my Fe3? Oh, look at that. We're doing well. The 1/3 Fe3O4, those also cancel. Oh my gosh, nothing else cancels. Now I've got to figure out how these all add up. So, let's see. I've got my Fe right here. I've got, let's put the CO2s. I've got some CO2s here and some CO2s here. I've got 3/2 on the left and 1/3 plus 1/6. 1/3 is 2/6. This is 2/6 and 1/6. So together these make 1/2 of a CO2. And I had 3/2 of a CO2 on the left. So that means I'm left, hopefully you see the 3/2 minus 1/2. I'm left with 1 CO2. Oh my goodness, that's how many I needed. That worked out quite nicely. So I've taken care of my CO2s. Now my FeO, I only have one of those. Oh goodness. And I need to figure out my carbon monoxides now. So new color. I've got some CO here, here, and here. I've got my 1/6 and 1/3. I already did that on the other side. These together make 1/2 of a CO. And on my right side, I've got 3/2 of a CO. 3/2 minus 1/2 leaves me with a single CO. Lo and behold, oh my goodness, it worked. The reaction that I was looking for is what I got. This reaction and this reaction do match. So now, whatever I did to the reactions, I do to my delta H's. So I have -1/2 of -23 minus 1/6 of 39 plus 1/3 of -18. -1 kilojoule. How strange. It's a very strange, very small heat change occurring for the reaction. And there's a big mess here, but ultimately, delta H for this reaction is -1 kilojoule, and sig figs, I keep to the ones place. I'm good, and that's it.